These are the formulas you will need to know for your quiz on section 9.4 and 9.5. You can think of them as a memorization thing if you like memorizing, or you can go back and look at the older videos for how to get the formulas without having anything memorized. And that's what I'll go over first. So you walk into the quiz, your mind has gone to blank, you don't know any of the equations. Here's how you can do the problem without knowing most of the equations. The first term is 18. The second term is 18 minus 5. And the third term is 18 minus 5 more. And the fourth term is 18 minus 5 minus 5 minus 5. And so to get this equation, I take the first term, minus 5, and I figure how many 5s to minus. So if you think of the second term, I minus 5 once, and the third term, I minus 5 twice, and the fourth term, I minus 5 3 times. I have to minus one less 5 than the number of terms. So there's a way for you to get the formula without knowing the formula. If I were to write this, and then let's figure out all the information. I know my first term is 18. I know my last term is negative 37. I know the formula for the number of terms is 18 minus 5 times n minus 1. And if I want to make that look nicer, I can do that as 18 minus 5n plus 5, which is negative 5n plus 23. I don't know my number of terms, though, so if I wanted to figure that out, I would have to do a little bit of work off to the side. If my last term is negative 37, and my formula is negative 5 times the number of terms plus 23, I could solve this equation. If I subtract 23 from both sides, I get negative 60 equals negative 5n, and that's n equals 12. So now, without knowing the formula, I actually have everything I need. I've got the first term, I've got the last term, I've got the formula, the explicit formula, I've got the number of terms. So I've got all of this stuff. And now, if I wanted to answer the question, in summation notation, I could say that the sum from the first term to the 12th term of the sequence generated by negative 5n plus 23 is equal to, and now we're going to pause here. When you're writing this notation is this sequence. That's just a fancy notation for this sequence. But if I actually wanted to find the sum of the sequence, I'd have to take the first term plus the last term divided by 2 times it by the number of terms, that's 12. And so for that problem, I'm going to take 18 minus 37, which is negative 19, times it by 6, I get negative 114. So the sum of the series is a negative 114. Now I know this was just review, but that's going to be a couple of the questions on the quiz, one arithmetic, one geometric, figure out what the formula is, write it in summation notation, and I was able to do that problem without having memorized the explicit formula for arithmetic sequence because I could think through it by patterns and working it out. So now let's talk about what's new. What's new in this section is we're actually going to talk about converging and diverging. So one thing that's good to know is that all arithmetic sequence diverge. Diverge, think of it just means this sort of gets really big or goes a little bit crazy. So what I mean by getting big is if I took 1 plus 3 plus 5 plus 7 plus 9 and I just added those up forever, that would eventually just boom, it would head off to infinity. So things that get big go to infinity. Things that don't get big are like this. If I took 8 and I added 4, and then I added 1/2, then I added 2, and then I added 1, and then I added 1/2, and then I added 1/4, and then I added 1/8. I'll show you why in just a minute, but this is an example of a convergent series because I'm adding a smaller number each time, 0.5, 0.25, 0.125, and because each number that I add gets smaller, this series is eventually going to converge on a single number. So let's just take a look at a couple of series. Let's say I had 16 times -2 to the n minus 1 power. So the first term would be 16, and then it would jump down to -32, and then it would jump up to +64, and then it would jump down to -128, and if I take 128 times 2, it would jump up to +256, and this would be just going down, up, down, up. So that's what I mean by going a little crazy. It just gets bigger and smaller and smaller and bigger, and the numbers just get huge. And this series is geometric, but it diverges. Now let's take a look at that series I said that was convergent a minute ago by looking at partial sums. The first number is 8, and the second number was 4, so the partial sum there is 12. And the third number was 2, so the partial sum there is 14. And the fourth number was 1, so the partial sum is 15. And the fifth number was 1/2, so the partial sum is 15.5. And the next number was 1/4, so the next partial sum is 15.75. And the next partial sum was 1/8, that's 0.125. If I add 0.125 to this, I get 15.875. So what I'm looking at is if I just were to add this up forever, what number would it eventually approach? And I'd like you to try this on your calculator by doing second stat. I'm going to take the sequence of 8 times 1/2 to the x minus 1 power. Put that in for x, and let's just say I do this 50 times. And if you remember, we talked about hitting enter here and then finding the sum of the answer. Take a moment to do that. And I get the answer on my calculator as 16. And if I add up the first 100 terms, I still get an answer of 16. And if I add up the first 1,000 terms, I still get an answer of 16, because what happens is this graph is approaching an asymptote of 16. And instead of doing these all separately with the big formula, I can replace it with this new formula that says the sum of an infinite geometric series that converges is the first term divided by 1 minus r. And if I take the first term, 8, and divide that by 1 minus 1/2, I get 8 divided by 1/2, which is 16. So there's your new formula for the sum of an infinite geometric series. Now, if the geometric series is like this, 2 times 3 is 6, times 3 is 18, times 3 is 54, then that series is not going to converge because it's going to get bigger forever, and this would be an example of a divergent series, and you don't have to find the sum if it's divergent. So the last thing we're going to look at is how to use series to simplify decimals into fractions. So let's take 8.141414. This is an infinitely repeating sequence, and so we can use repeating decimals in the formula that the sum of it infinitely repeating converging geometric sequence is the first term over 1 minus r. Use this formula to make this into a fraction. So this is going to be 8 plus 14 over 100 plus 14 over 10,000 plus 14 over a million. Or maybe that's 10 million. Nope, it's a million. And so if I look at that, not the 8, sort of like ignore the 8 for now. But if I look at the other part, this is 14 over 10 squared. This is 14 over 10 to the 4th. This is 14 over 10 to the 6th. This is a converging series. And the first term is 14 over 100. And the common ratio is 1/100th. And if I simplify that, that's 14 over 100 over 99 over 100, which simplifies to 14 over 99. And if I just toss the 8 back in, I end up with 8 and 14 over 99. Now you can double check that on your calculator, but if you take on your calculator 8 plus 14 divided by 99, it comes out 8.14 repeating. So I just use a convergent series to turn this into this. The Mrs. Search showed me another nifty way to do this, that if you let x equal to 8.14 repeating, if you move the decimal over 2 places, that would be the same as 100x is equal to 814.1414 repeating. And then if you were to take the first equation and subtract the second equation, you'd end up with 99x equals, and then these ones right here would cancel these one right here, and so it would end up with 814 minus 8, which is 806, and so x would be equal to 806 over 99. And if you check your calculator, 806 over 99 is equal to 8.14 repeating. So there's an alternate way of getting it that doesn't use series, but it's kind of fun. Let's do one more example of that. Let's say you had 3.22222 like this. And some of you actually have that memorized, probably. That's 3 2/9. But if you don't have it memorized, 3.2 repeating, and you had to turn it into a repeating decimal, this would be 3 plus 2/10 plus 2/100 plus 2/1000. And so if I ignore the 3 and I'm just looking at this series, the first term is 2/10, and the common ratio is 1/10, so 1 minus 1/10. So this is 2/10 over 9/10, which is 2/9. And so if I add the 3 back in, I get 3 2/9. And prior to the days of calculators, it was really nice to know how to do this so you could be able to change a repeating decimal to a fraction without having a calculator in your hand. Now it's just sort of a nifty trick when you don't have a calculator handy. So what I want you to do is look at this page, and if these were series, which series would converge? There's only one of them on the piece of paper. how you think through it is ask yourself, are they arithmetic or are they geometric? If it's arithmetic, it's going to diverge, so you don't even have to think about it. If it's geometric, it could diverge or it could converge. It's going to diverge if the ratio is bigger than 1. It's going to converge if the ratio is between -1 and +1. And so when I look at these, this is arithmetic, so it diverges. This sequence right here is subtracting 2 each time. That's arithmetic, so it diverges. This sequence up here, it's getting multiplied by 3 each time, so that's just getting bigger, so it diverges. This sequence right here, it's getting multiplied by -2 each time. It's getting bigger than smaller, then bigger than smaller, then bigger than smaller, then bigger than smaller. So this one diverges. So we've got divergent, 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 divergent. There's only one sequence that's converging. The common ratio right here is 1/3 each time I'm dividing by 3. 6 divided by 3 is 2. 2 divided by 3 is 2/3. 2/3 divided by 3 is 2/9. So this is the only one that has an infinite sum, and the sum of this sequence is 6 divided by 1 minus 1/3, which is 6 divided by 2/3, which is 9.